7C is all about the law of large numbers. So this is basically what we're talking about for the theoretical and the empirical probability, where the theoretical probability is like in the long run, this is what's supposed to happen. So this is the long run. So this is saying that the more times you do it, the closer and closer you get to that theoretical probability. So for example, if you toss a coin 4 times, and you only get one head, then the empirical probability there is you got a head 25% of the time, which, theoretically you should get it 50%, right? But with just the short number, you're not guaranteed that, right? Because like we talked about, there's a lot of variables, a lot of things that happen which can influence it. So if you only tossed a 4, it's possible to get one head. There's a 25% chance that you get a hit. Or you got a head 25% of the time. Now if you toss it 100 times, you might get 64 heads. Well, that's 64% of your tosses were heads, which, now is on the other side of the 50%. Well, if you toss it 1,000 times, you might get a head 582 times. Well, that's 58.2%, so that's even closer to that 50. But if you toss it 10,000 times, you might get heads 4989 times, which is even closer to that 50%, so 49.89%. So the more tosses you do, the closer and closer this gets to 50%. And if you've taken any other stats classes, this can be called the regression to the mean. But we're not going to talk about that. So the law of large numbers is saying that the more you do, the closer it is to theoretical. The more all of those little variables don't make a difference. Okay, so we use this law of large numbers to help us make decisions. So I talked about like the insurance companies, where they look and see how often people have filed claims in the past to help them try to guess how many people are going to file claims in the long run. And so we'll look at an example for that as well. But expected value is basically your average expected payoff in the long run. So if you were to do something repeatedly, this is what you would expect to happen each time. Doesn't mean that it's guaranteed to happen that time, but it's just saying, overall, if I kept doing this, this is how much I would get each time, or lose this time. So for the first example, let's say your school is raffling off a season pass to a local theme park, and the value of that pass is $200. If the school sells 1,000 $10 tickets, each person who buys a ticket will lose $9.80. So that's like your expected value is $9.80, except for the person who wins. So overall, it seems like it's a loss for you, even though the school's going to get a lot of money behind that, right? So you might want to save your money, but again, that's up to you. A school's raffle is a good cause. It's only $10, but that's beside the point. So basically, to figure that out, what we're going to do is we're going to look at our two options, whether we're going to win the ticket or we lose the ticket. So if we win the ticket, then the value to me is $190, because I've spent that $10, I don't get it back. So that season pass then would be worth to me $190. The probability that I'll actually get that is 1 out of 1,000, so one ticket out of the 1,000 they're selling. So if we take that theoretical probability, so if the odds are that I get 1 out of 1,000, that I get that 190, we multiply them together, and so that's a 0.19. Okay, so let's set that aside for a second. Now let's consider the probability that we lose. Let's talk about the probability that we win. The probability that I lose are going to be the other 999 out of that 1,000, right? So the odds of ending up just losing the $10 is 999 divided by 1,000. So if we multiply this probability times my losing $10, I get negative 999. Now we're going to combine the idea of like weighted means, because we have a different probability times the value, just like we have like the weight of the grade times the actual grade. And we're going to add these two together, so 0.199 plus the negative 9.99, and we end up getting a negative 980, which is where that comes in. So the general rule of thumb, if we want to find the expected value of one game or one thing we're looking at, that's going to be your first event times the probability times the value of your first event, plus the probability times the value of your second event, and so on, depending on how many events you have. That will encompass all of your possibilities. So in this case, the expected value would be the probability that we win, and the probability that we lose, and then the value to me for both of them. Either I win $190 or I lose $10. So the probability that we win was going to be 1 out of 1,000 versus winning 190, so that would be positive 190. The probability that I lose is 999 out of 1,000 times losing $10. We put that all together, it would be negative 9.8. Okay, let's look at another example. So let's say now we're rolling a fair die, and this is what happens with the result. So if I get a 1, I'm going to win $3. I get a 2, nothing happens. A 3, I lose 5. A 4, I win 3. 5, I lose 4. And 6, I win 2. So is this a good game for you? Should I play this? So what is the expected value for one game? So if I were to play this over and over and over again, what should I expect to get or lose per game? So I am going to set up a little table here. I'm going to list out all of the events that could happen. The probability of that event happening and the value to me. So what I get or lose. So the event, I could roll a 1, I could roll a 2, a 3, 4, 5, or 6. So those are all my possible events. The probability of any of these happening is going to be 1/6. The value. So if I roll a 1, I win $3. I want a positive 3. If I roll a 2, nothing happens. So I don't win, I don't lose, it's just a 0. For 3, I lose 5, so I'm going to subtract 5, or negative 5. If I roll a 4, I'm going to win 3. If I roll a 5, I'm going to lose 4. If I roll a 6, I'm going to win 2. So the expected value for this one game is just like weighted means. I'm going to take my weight times my value, so 1/6 times 3, plus 1/6 times 0, plus 1/6 times negative 5, plus 1/6 times 3, plus 1/6 times negative 4, plus 1/6 times 2. So I put all of that in the calculator and I end up with a negative 0.17. Note also that all of these have the same weight, so really I could have just added all these up and divided by 6. Right? When we talk about if everything has the same weight, then it's just like a normal mean. So as long as you have all the values, you could do that. But to be on the safe side for stuff like this, you can just write them all out individually. Okay, so the expected value for one game is a -17, which means that if I played a lot of these games, I would, on average, lose 17 cents per game. Well, that doesn't really seem like a great game for me, so I'm going to say no, it's not a good game for me. I mean, it's possible I could roll a 3 right off and I will lose 5. That's bad. Or I could roll a 4 straight off and get a 3 and get $3. So, I mean, I could just keep rolling the wins, but probability says that overall I would lose money in this game. So we talk about like if we had a lot. So if I played this game 500 times, so this is a lot, right? So if so the law of large numbers applies. So if I played this game 500 times and on average I lose 17 cents per game, then I can multiply these two together. So 17 cents per game for 500 games. And I might lose $83.33. So I'm gonna pass on this game. Okay, example 3. You're given a 7 to 2 odds against rolling 2 even numbers with the roll of 2 for a dice. Okay, so in this case, we have this odds against, but this is not quite the same thing as the odds we've been talking about before. That's why they are going to explain it here. So betting odds is a little bit different. So 7 to 2 odds against rolling 2 even numbers means you get 7 if you succeed and you lose 2 if you fail. And these are all the possibilities for your first roll here and your second roll here. So the first roll you get a 1, second roll you get 1 through 6. If you get a 2, you can get 1 through 6 for second roll and so on. Okay, so again, I'm going to set up my table. Find my event, my probability, and its value. Okay, so I'm wanting to roll 2 even numbers. So the event is I could either roll 2 even numbers or I could not roll. I could roll an odd number. At least one odd. So we need to figure out the probability. It's the probability of rolling 2 evens. Well, okay, the first of all, I can figure out how many are total, right? So I could roll, there are 6 possibilities for the first, so 2 rolls. There are 6 possibilities for the first roll, 6 possibilities for the second roll, which means there are 36 total. So how many of them are 2 evens? Well, I could, again, we have 2 rolls. How many evens are there for the first roll? Well, there's 2, 4, and 6. There's 3. How many evens for the second one? 2, 4, and 6. There's another 3. That's 9. So 9 that have evens over 36 total. So a simplified fraction would be 1/4. So probability of rolling 2 evens is going to be 1/4, which is the probability of rolling at least 1 odd or not rolling 2 evens is going to be 3/4. Okay, so if I do roll 2 evens, that means I get $7. And if I don't roll 2 even numbers, I lose $2. Okay. So now we can find the expected value of the game. The expected value for one game. I take the probability times the value of each one. So 1/4 times 7 plus 3/4 times -2. So if you're going to put this in the calculator, just be careful with fractions. All of these are multiplication division, so you could just put 1/4 times 7, or 1/4 parentheses 7, and you'd still get the right answer, but you just have to be careful. I would suggest anytime you have a fraction to put it in parentheses. So you'd have 1/4 times 7 plus 3/4 times -2. Just so you don't get like the order of operations messed up in the calculator. You'll have to be on the safe side. So all total, this would add to 0.25. So this is in dollars. So that means that I would, on average, expect to win 25 cents each game. So if I were to roll a bunch of times, I would expect to win on average a quarter each game. So if I played it 250 times, if I get 25 cents for each game and I play that 250 times, then I could expect to win $62.50. Now, am I guaranteed to win that? No. This is just, expected. In the long run, this should be what it is. So average over 250 games, you should expect to win $62.50. Okay, example 4. Here's the insurance I kept talking about. So the insurance policy sells for $1,200 based on past data, right? So our empirical probabilities here. An average of 1 in 100 policyholders will file a $20,000 claim. An average of 1 in 200 policyholders will file a $50,000 claim. And an average of 1 in 250 policyholders will file a $50,000 claim. Oh, that was a typo. I forgot to change that. Let's change this one to 30,000. I need to fix that typo here. Let's say 1 in 200 will file a $30,000 and 1 in 250 will file a $50,000 claim. From the expected value to the company per policy sold. And if the company sells 10,000 policies, what is the expected profit or loss? Okay, so I'm going to set up my table. So I have my event, the probability, and the value. Okay, so think about everything. So one of the events is that the insurance actually sells their policy, right? Because they have to sell it before the customer can do anything to it, right? So there's event sell it, and there's a possibility that the policyholder will submit a claim. Okay, so the probability that the insurance company will sell this, we're going to say is 1, because of course they can't file a claim without actually selling something, so there's a 100% chance that they're going to sell it. Now the claim. So there's actually 3 different claims. So we'll say claim 1, claim 2, and claim 3. So claim 1, this $20,000 claim, there's a 1 in 100 chance that that will happen. And the second claim that I mentioned, there's 1 in 200 chance. And the third claim, there's 1 in 250 chance. Okay, so the value to the company, if he sells an insurance company, they're going to get $1,200 no matter what. And that's going to be money in. So for this first claim, if they file this first one, the company is going to lose that $20,000. And that's going to go to the customer. Now the second claim, they're going to lose $30,000. And this third claim, they're going to lose $50,000. Okay, so the expected value for one policy for the company, we're going to multiply all these together and add them up. So we have 1 times 1,200 plus 1 over 100 times negative 20,000 plus 1 over 200 times negative 30,000 plus 1 over 250 times negative 50,000. And you're going to put that in my calculator with parentheses around all of the fractions. And I get 550. So on average, the company should expect to gain $550 per policy. Now, if the company sells 10,000 policies, expect to win or to gain $550 per policy times 10,000. You're going to end up with $5.5 million. Right, it's because this comes out to be 5,500,000. So $5.5 million profit, which is why insurance companies make a lot of money. Okay, last example. Back to the lottery Powerball. So the table below gives prizes and probabilities of winning on a single $1 ticket for the multi-state Powerball lottery. Find the expected value of the winnings for a single lottery ticket if the jackpot is $30 million. How much can you expect to win or lose each year if you buy 10 lottery tickets per week? Should you actually expect to win or lose this amount? Okay, so fill in the table. So here's all the different prizes you can get from that $1 ticket. And this is the probability of getting each of those prizes. Know that the jackpot is 1 in 292 million. Okay, so the value. If you win the jackpot is 30 million. So if you win it, you're going to get $30 million. Okay, the probability, of course, 1 in that means that this is, the probability is going to be 1 over that. It's 1 divided by that. So if you win the 1 million prize, value to you is, of course, $1 million. And then you have the $50,000 prize, $100 prize, you get 100, 107, 7, 4, and 4. But of course, you also have to buy the ticket, right? So the probability is 1, and the value is a -1. Okay, so you could do it this way and have that 1 times whatever here. You could also do like what we did for that first example, is just take off that 1 from all these values. So this would be 29,999,999. So 999,999, 49,999, 9999, 66, 3, and 3. So you could do that if you wanted to. But I'm just going to keep it as separate so I don't have to have all those numbers. Okay, so then we take 1 over this number times 30 million. And we get 0.1027. 1 million times 1 over that number. And we get 0.0856. 1 over this number times 50,000 gives me 0.0548. 1 over 36,525 times 100 gives me 0.0027. So just to, right, so we'd have 1 over 292,201,338 times 30 million to get the 0.1027. Okay. And I'm going to keep it out as 4 because I want to eventually round to the nearest cent. So I want to make sure to not have that rounding issue. Okay, so continuing on, we have 1 over 14,494 times 100, and we get 0.0069. 1 over 580 times 7 gives me 0.0121. 1 over 701 times 7 gets me 0.0100. 1 over 92 times 4 gives me 0.0435. And 1 over 38 times 4 gives me 0.1053. And lastly, probability of 1 times the value of -1 gives me -1. Okay, so now I'm going to add all of these up. And I would end up getting a negative 0.5764. And that is my expected value for 1 ticket. So the expected value for the winnings is going to be a negative 57 cents, or 58 cents if I'm rounding. In other words, average over many tickets, a lottery player should expect to lose 58 cents for each lottery ticket. So, what does that mean? So if you bought a lot of tickets, on average, you're going to lose money for each one instead of gain it. So if you buy 10 lottery tickets per week for entries, you can expect how much in a year. So first we need to know how many tickets are we going to buy in a year. So we buy 10 tickets per week. There are 52 weeks in a year. weeks canceled, so I'm left with 10 times 52, so it's 520 tickets per year. So I want the expected value for 520 tickets. So I have a negative 58 cents times 520. And I'm going to expect it to lose because it's going to be a negative $301.60. That's a lot of money, right? So worst case, if you don't win anything, you lose $520, right? If you buy 520 tickets. Best case, right? You get all sorts of prizes, but most likely you're just going to end up losing about $300 for that year. And that's it for 7C.